So we're here in Chapter 3, Section 3, talking about projectile motion. So let's take a look at a sample problem for projectiles launched at an angle. Now, please be aware, I did not write this sample problem. It is just pretty bad. Okay, the problem's fine. The story's annoying. Here we go. A zookeeper finds an escaped monkey hanging from a light pole. Aiming her tranquilizer gun at the monkey, she kneels 10.0 meters from the light pole, which is 5.00 meters high. The tip of her gun is 1.00 meters above the ground. At the same moment that the monkey drops a banana, the zookeeper shoots. If the dart travels at 50.0 meters per second, will the dart hit the monkey, the banana, or neither one? Okay, so that's pretty darn contrived, but let's see what we can do in terms of a physics problem here. Pretty much everything, you want to select a coordinate system first. Okay, we need to be able to take into consideration not just magnitude, but also direction. And things like north or east or up or down, they don't help us when we're actually doing calculations. And so by establishing a coordinate system, we know whether or not to use a positive or negative sign convention. So typically, this is what I do in this class, the positive y-axis points up and the positive x-axis points along the ground toward the pole. Because the dart leaves the gun at a height of 1.00 meters, the vertical distance is 4.00 meters, as you can see in this diagram here. Step number 2. We can use the inverse tangent function to find the angle that the initial velocity makes with the x-axis. So again, if I go back to our diagram here, we're going to use the inverse tangent function to find this angle here. Okay, the gun is aimed somewhat up, right, at this particular angle. What is this angle? We are going to use the inverse tangent function to figure out exactly that. Again, this is why it's so important to draw a picture for yourself when you're setting up these problems. Because, again, just kind of pulling this out of the thin air can be tricky for a lot of students. But if you always have this diagram to look for, it's easy to define your tangent, your opposite over adjacent. Okay, tangent. So taking the inverse tangent of 4.00 meters over 10.0 meters, you get 21.8 degrees. So we have the direction here. We have the theta, the angle. Next, let's pick one of the kinematic equations that'll allow us to solve for time. So we're going to rearrange the equation for motion along the x-axis so that we can isolate the unknown at delta t, which is the time the dart takes to travel the horizontal distance. Okay, and you know that once the dart is launched, it's traveling at a constant velocity. The velocity is not changing. Therefore, acceleration is numerically equal to 0. And that allows us to actually cancel out the entire second half of this equation, right? The 1/2 at, right? The 1/2 times acceleration times change in time. Because that acceleration is equal to 0 numerically, that whole part of the equation cancels out. And so we're left with kind of the front half of that particular equation, which is delta t is equal to the initial velocity multiplied by the cosine of the angle. Cosine, because we are looking for the horizontal distance, right? The delta x. And the x side of that triangle is the adjacent side relative to the angle. So that makes it cosine. We can rearrange that equation to solve for delta t like we already mentioned. And so it would look like delta t is equal to delta x divided by the initial velocity multiplied by the cosine of theta, the angle. Once we actually have the equation solved for delta t, which is what we want, we can plug in those numbers. So there's our 10 meters divided by the 50 meters per second multiplied by the cosine of 21.8 degrees because we just figured out theta in our previous step. And we come up with a time of 0.215 seconds. Again, we're using 30 sig figs here because everything in that question, that horrible, horrible question, had 3 sig figs. Next up, let's find out how far each object will fall during this time, right? The time that we just figured out. So we'll use the free fall kinematic equation in both situations. So we can think about the banana. The initial velocity is 0, right, because it was dropped. Therefore, we can set up our equation 1/2 acceleration. In this case, it's acceleration in the y direction, so that's going to be equal to gravity. It's going down, so we're going to have to use a negative sign in there, times the change in time squared. Okay. Now, you might notice that usually this kinematic equation has kind of that front half, that initial velocity times time. Well, we just established that initial velocity is 0, and well, when you multiply anything by 0, it's 0. So we actually kind of get to ignore the front half of that equation. Ends up being kind of convenient because this is a lot easier to solve for, to be perfectly honest. So this change in y, right, the y system, sub b for banana, right? So the delta y for the banana ends up being negative 0.227 meters. So the dart has an initial vertical component of velocity equal to the initial velocity multiplied by the sine of the angle, because again, the vertical component, that y component, going back to our triangle, is opposite the angle, right? So opposite over hypotenuse, that's sine. And so we can actually calculate the delta y for the dart. Okay, again, initial velocity times the sine of theta, right? And we already calculated theta, times delta t, right? But we also already calculated delta t, plus 1/2 a in the y direction, which again going to be gravity in the downward direction, so negative, multiplied by that same time squared. So we can plug in those values. We have our initial velocity of 50 meters per second, multiplied by the sine of 21.8 degrees, multiplied by 0.215 seconds, plus 1/2 the negative value of force of gravity, or acceleration due to gravity, rather, multiplied by the time, which is 0.215 seconds squared. We can simplify that down a little bit. Kind of the front half of that equation ends up calculating to 3.99 meters. The second part of that equation ends up calculating to a negative 0.227 meters. And again, taking the difference, 3.76 meters for that vertical component of the dart. So last step, let's consider our results. Okay, we find that the final height of both the banana and the dart are pretty darn similar. Okay, pretty darn similar. Notice that's a 4.77 meters above the ground for the banana and 4.76 meters above the ground for the dart. And so, because these are essentially identical, the dart will actually hit the banana. There's a slight difference. That's why you see a 4.77 versus a 4.76, but that's due to rounding in the intermediate steps. But you see they have the exact same, again, I know due to rounding it's a little bit off, but essentially the exact same delta y, right? That y component, and so that dart will actually hit the banana.